Hello, everybody. Now it's time to start. Sit down, please. Today there is lecture number 13. And we will discuss theory of variations. Okay, first of all, we will speak a little about functionals. Functional. Do you know this word, a functional? A function, do you know what is the function? A function. Function is a correspondence. It's a correspondence between a set. Yes, if we speak about a function, so a function f from x to y. This means that given two sets x and y. Okay. So given two sets, we know the correspondence that associates a unique value y from the set y capital to each element of x capital. Yes, so this is a function. It associates a y, a unique y, to any value x. x1, x2 goes to y2 and so on. This is a function. And the functional is a function also, but a functional is a function that associates a number with a function. So x, a functional, associates a number to a function. So we take a function f, some function, and associates and we associate a number to functions, right? So the arguments of these functions is function. So the arguments are functions. Well, for example, if we speak about if we consider a plane and we consider not points in R2, right? If we consider points, then we speak about multivariable functions. Yes, each point goes to some number, right? This is called a two-variable function. Yes, but if we consider different objects in R2, if we consider, for example, all the rectifiable curves, yes, let's consider a rectifiable curve, for example, yes. And we can compute the length of this curve, right? And if we associate a number with any rectifiable curve, then this is a functional. This is a functional. It associates a number to a rectifiable curve, right? So to an object, more complicated object than a vector, finite dimensional vector. Okay. So operator, so I will define it. So we will speak about problems such as minimization of maybe of length. Yes, for example, in our example, if we fix 2 points, so A will be, so let's fix 2 points A and B, and suppose so this is alpha and this is beta. So if we fix 2 points and if we consider a set of the set of all rectifiable curves joining these 2 points, we can consider function. So now we can write the functional. Suppose any curve is described by a function y equals, let it be y of x, let it be a function, and then we can associate to any function y of x the length of this curve. And if we speak about only smooth curves, yes, then we need to associate a number, so the length of the curve. What is so the arc length integral is equal to 1 plus y prime squared, yes, dx. Yes, and this is a functional. Yes, it is denoted. We will denote it by g of y. So this functional associates a number to any function y. Okay, so the argument not a point but a function. Yes, a function. Well, so and if we want to minimize this, so usually in physics and in mathematics and in physics in particular, we consider the problem of minimization of such functionals. And what is the solution of this minimization problem? Do you know? If we fix 2 points, what is the shortest path? A straight line, yes. So the segment of the straight line. But how to prove this? Analytically, do you know? This is all only our intuitive. So our intuition, yes, or maybe. So we were spoken that this is the answer, the shortest distance. Calculus of variations, yes. And now we will discuss the problems of this nature, and yes, we will try to develop theory of variations. We will try to solve the problems of such kind, and okay, obtain the Euler Lagrange equations. Okay, have you heard about this, Kathy? Yes. So theory of variations, Euler Lagrange equation. Yes. Okay, and now we will speak about this. Right. Let's discuss theory. Now we need to develop an analytic approach to solving these problems, the problems of this kind. Okay. There are various problems of minimization or maximization problems. For example, we can consider the problem, it is called the minimal surface problem. If we, for example, fix the boundary and we are looking for so the surfaces with this boundary, with this given boundary of minimal area, for example. Yes, so in these problems we must fix the boundary, but now we will consider the simplest the simplest class of variational problems when we when the function y is assumed to be differentiable. Yes, so we will look for the function y of x. So our goal was to find the function y of x, which is of class C1. minus on AB. We will consider the functionals of the form, so the integral from A to B. And so in our example, we have the function which is equal to the root of 1 plus y prime squared. But we will consider more general class of functions, L, depending on x, y, and y prime, dx. So we suppose that this function, the integrand, depends on x, y, and y prime. And this function is called the Lagrangian function in honor of Lagrange. And so it will also be of class C1. And we fix the endpoints. Yes. So we will consider, we will look for the functions y of x, which are of class C1, and satisfy boundary conditions. So y of A must be equal to some value alpha. It is fixed. A and alpha are fixed. And the second condition is y of B equals beta. So given numbers A, alpha, B, and beta, and given the Lagrangian function, we are asked to minimize this functional. Okay, and we will try to solve this this problem. Okay, so today we will discuss the critical points, finding critical points for this functional. What are critical points? We want to generalize our common common intuition, maybe concerned with critical points. So, for example, if we have a function, right? So now I am trying to explain what are critical points in this case. So, given a multivariable function, so multivariable calculus, and suppose f is a function depending on several variables. So f is just a function, not a functional, a function. And we are looking for critical points of f. What does it mean, critical point of f? So we must find the gradient of f is equal to the first derivatives with respect to so x1, x2, dot f prime xn. And we equate this gradient to 0, and then x0 is a critical function, is a critical point. So x0 is called a critical point if the gradient of our function is 0. So we assume that our function is a differentiable function. Yes, and we will try to find the analogy of this equation for the functional, when the arguments not n-dimensional vectors but functions. Okay, what is the analogy of the gradient? So for the gradient, we need n variables, and we're trying to find the partial derivatives with respect to each variable, right? Let it be xi and equate to 0, but this space is not finite dimensional. So this is the specific of an n-dimensional finite dimensional space. We need a finite dimensional space to do this. but here we have an infinite dimensional space. Yes, and so to introduce a similar notion in the infinite dimensional case, so we will do the following. We will try to represent this definition using any directional derivative, using directional derivative. Okay, so what is that directional derivative, right? So if v, vector v, represents a direction, okay, then the directional derivative yes, derivative. Yes, this is so if our function is differentiable, then it is the inner product of nabla f of x, let it be x0 and v, and from the other hand, so by definition, it is equal to the derivative of so it is f of x0 plus epsilon v taken at the point epsilon equals 0. And then we can say that nabla f is 0 if and only if this directional derivative is 0 for any vector v, right? For any v. So we must take directional derivatives. Right? So this is a vector. And if this directional derivative is 0 for any vector v, if it doesn't depend on vector, then nabla f is a 0, so is 0. And so x0 is a critical point. Okay. Using the same reasoning, so now let's try to apply the same similar arguments to construct the directional derivative for a functional. Well, what about the inner product? So if we try to find to find nabla j of y, what does it mean? So first of all, let's discuss the inner product. So in finite dimensional case, v is a point, is a vector in Rn. Yes, is a vector in Rn. Here v is a function. It is also a function. V is a function. Okay. So first of all, we must introduce the inner product. What do you? So do you know how to introduce the inner product in the space of functions? What are your suggestions? How to define the inner product or dot product in the space of functions for functions? Do you know? Huh? No. So we must use the integral, yes, because we need to integrate. Okay. So using the integral, so the integral from a to b of f times v. So this is the product of two functions. So we must multiply them and integrate to this. So this is the inner product. Well, this the inner product, and so this will be defined as the integral from a to b nabla g of y times v dx. Okay, and now we want to use the second formula, this one. How to use this formula? How to use this formula? Let's try to find the derivative d over d epsilon of g of y plus epsilon v. So we multiply our function by epsilon. So v is called a variation in y. So v is called a variation because we vary. Y is varied. Yes, a variation in y. And sometimes it is denoted by delta y. Okay, but we will denote it by v. Okay, how to compute this? Epsilon equals 0. How to compute this? So we know that this is, I will rewrite it in the form d over the epsilon L of x, y prime dx. So we must add epsilon and then differentiate. The x. And then substitute epsilon equals 0. What shall we do to find the derivative? Okay. Since we are operating with smooth functions, yes, this is the segment, and all the functions are of class C1, and L is a differentiable function. L is also of class C1. We can move the differentiation inside the integral. So we will differentiate the integrand with respect to epsilon now. Yes, and it will give us the following: the integral from a to b. Then let's differentiate this with respect to epsilon. So to do this, so L depends on 3 variables, 1, 2, and 3. So we must differentiate the second variable with respect to epsilon, and this will give us v times dl over dy. Okay, and substitute 0 for epsilon, so it will be d over dy of, I will write it as L x y prime. Yes, this is the partial derivative of, so using the chain rule. Yes, using the chain rule. And next we need to differentiate the second, so that the third component of L. Differentiate this with respect to epsilon, and this will give us plus v prime d over dy prime. This means that we differentiate L with respect to the third argument, d of x, y, and y prime dx. The square bracket. Well, okay, so this expression is called a variational derivative. Variation. Okay. And now for our function y to be a critical point, so by definition, so by definition of a critical point, we want this integral to be equal to 0, right? A variational derivative must be equal to 0. Okay. So I want to make some conclusion about this function, this integrand, yes, this expression. And to do this, I want to represent our integral in this form. So these are two formulas for the same notion, and so I want to represent this integrand in the form where some function is multiplied by the function v. Yes, by the function v. Now we have only this part multiplied by v, but this part is multiplied by v prime, and so we want to eliminate v prime and rewrite this second part of the formula as the product of v and some other function. And so now my goal is to rewrite this part as to represent it as the product of v by some other function. And now I will do this. I will try to do this. Now let's consider the integral, the second part of this formula, the integral from a to b, b of v prime d over dy prime L of x, y and y prime dx. I want to use integration by parts. And so to apply the formula of integration by parts, I will move v prime to the differential, and I will rewrite this formula as the integral from a to b d over dy prime L dv. Okay, and it is equal to, so by the integration by parts, the product of v and this function, dl over dy prime, from a to b, minus the integral from a to b, v times the derivative d over dx of d over dy prime L dx. Well, and now let's discuss this first part. So it is equal to v of b times dl over dy prime at x equals b minus v of a dl over dy prime at x equals a minus the integral from a to b v d over dx d over dy L dx. Okay, now let's discuss the function v of x, the variation in y. I state that v of a equals 0 and v of b equals 0. This is because we consider the functions. We consider j of y plus epsilon v. And by definition of the functional g, the arguments for j must be functions such that y plus epsilon v of a is alpha and y plus epsilon v of beta, or of b is beta. And since y of a is also alpha and y of b is beta, it follows that v of a equals v of b equals 0. So our variation must satisfy this condition. V of a equals v of b equals 0. So this means that v of b is 0 and v of a is also 0. And so we are left with only this part of the integral. So this part. So our original integral is equal to minus the integral from a to b, v times d over dx of dl over d, so dy prime dx. And by virtue of this, so the last equality, we can rewrite our integral, our variational derivative, in the form here can be rewritten nabla j of y and v, it is equal to the integral from a to b nabla j y times v dx, and it is equal to the integral from a to b. And now we will substitute, so we will look at the formula, at this formula, the formula asterisk, and it is equal to v times dl over dy. But the second summand is replaced, can be replaced by this by the function of this form v times, so minus v times d over dx of dl over dy prime dx. And I will rewrite this in the form, the integral from a to b, v times dl over dy minus d over dx times dl over dy prime dx. So we have obtained this this equality. Okay. And we want this integral to be equal to 0 for any variation v, such that v is of class C1 and v of a equals v of b equals 0. It can be proved, but we will omit this proof, that if this is true for any variation v, then this function must be 0. Well, so this means that dl over dy minus d over dx dl over dy prime is 0. Okay, and this is called an Euler Lagrange equation. Okay. Is it time to have a break, or let's continue? Let's continue. Okay, so we have proved the theorem. I will formulate it, but we have omitted some complicated facts about, so okay, we have omitted the reasoning that allow us to obtain this equation from this statement. So if the integral of v times the function is equal to 0 for any function v, such that v is a differentiable function, yes, C1 function, and v of a equals v of b equals 0, then it follows that the second part must be 0. Okay. And so this is the way to find critical points. So in the sense of the function also. What is it?
Just by saying a and b can be arbitrarily small, so it's 0 at some point.
So v. So could you repeat? So v is not arbitrarily small.
Yeah, you can take the integral anywhere, at any point.
Yes, at any point, and
Total is 0. That means it must be uniformly 0 everywhere.
Yes, so almost. Yes. So the reasoning is just you say right. So, but for the rigorous proof, so I must suggest the way how to choose v. So suppose this function is greater than 0 in some point, then I can choose v to be 0 everywhere except for some small neighborhood at which it is also non-zero. So the way to explain this is the following. So suppose this is not 0, right? Suppose this is not 0. Suppose it is greater than 0 at some point. Yes. Then we are trying to choose v such that it is also non-zero at the same point and 0 elsewhere. Yes. So v of this form. So a, b, it is 0 except for this point at which this expression is non-zero. And then the integral of this product cannot be 0. Yes, so these are the reasonings. Yes, but I have decided to omit this lemma because I think it is too difficult maybe to give a detailed proof for this. There's a series of lemmas, right, of lemmata of such kind. So I will state the theorem. Suppose the Lagrangian function is at least twice continuously differentiable. Then any C2 minimizer y to the corresponding Lagrangian, to the Lagrangian C2 minimizer means that y is the function such that the Lagrangian, okay, so not to the Lagrangian, to the function, to the functional. The Lagrangian is the integrand. Yes, they're functional to the functional. G of y, which is equal to the integral from a to b, L of x, y, y prime, dx. Minimize means that y is such that the value of this integral is the minimal, the least among all possible integrals for all admissible functions. Okay, to the functional subject to boundary conditions, y of a equals alpha and y of b equals beta, must satisfy Euler Lagrange equations. It is necessary condition, but not sufficient. And in what follows, we will speak about sufficient conditions. Minus d over dx, dl over dy prime equals 0. Okay, so this is theorem. It was proved. And now we will try to apply this theorem to our example. Okay, so the minimal curve problem, joining two fixed points. So we fix points A, B, this is alpha and this is beta. And I recall that we consider the functional of the form, the integral from a to b. So the arc length integral, it is y plus y prime squared dx. And we want to minimize this integral. And the boundary conditions are the following. Okay. To solve this problem, we will write the Euler Lagrange equations. So Euler Lagrange equation. So first of all, what is dl over dy? dl over dy. How to compute dl over dy? So L is this function. What is dl over dy? Daniel, do you know? Does L depend on y or not? No. It depends on y prime, and so it is 0. It is partial derivative. Not total derivative, but partial derivative. What is dl over dy prime? So we must differentiate this function with respect to y prime. Okay, so 2y prime over 2 root 1 plus y prime squared. Y prime over root 1 plus y prime squared. Okay. And next, what shall we do next? So how to write the Lagrange equation? So we have just one. Okay, so next we must differentiate this. So the total derivative, we must take total derivative with respect to x. D over dx. How to find it? Okay, Daniel, how to differentiate this?
Good question.
Well, yeah, no, I want to hear from you, Daniel. Can you differentiate the ratio of two functions? Do you know the quotient rule? So the ratio of two functions. First, we need to differentiate the numerator. Okay, and what is the answer?
Going to be the denominator squared.
Yeah, so the denominator squared, yes. And differentiate this. Yes, times minus. Minus what? So we must y prime and differentiate this. Okay, and this will be y 2 primes over root 1 plus y prime squared. Yes. Okay, so to differentiate this, so it must be y prime times, okay, so y prime times y2 prime. Okay, is it clear? So because we differentiate y prime squared, so first 2y prime, so 2 is cancelled out, yes, y prime times y2 primes. Okay, next to simplify, simplification give us the following. It will be y2 primes 1 minus 1 plus y prime, yes, minus y2 double prime y prime squared over 1 plus y prime square to the power 3/2. And simplification will give us y double prime over 1 plus y prime to the power 3/2. Okay, what shall we do next? What to do next? Yes, so equate this to 0. So this is 0. And the Euler Lagrange equation will have the form minus y double prime over 1 plus y prime squared to the power 3/2 equals 0. And this is the same as y double prime equals 0. How to solve this differential equation? Y double prime is equal to 0. How to solve it? So first of all, y prime, so the derivative is 0, then c1, yes? And then y is equal to c1x plus c2. So this is the answer. Okay, and next, so our function must satisfy these boundary conditions. Well, let's solve the following. So y of a is equal to c1a plus c2 equals alpha. Y of b is equal to c1b plus c2 equals beta. And this is these simultaneous equations will give us c1 and c2, yes? Or not? What is c1? If we subtract, we will get alpha minus beta over over a minus b, and c2 is alpha minus a times alpha minus beta over a minus b. It is equal to alpha a minus alpha beta minus a alpha plus a beta a minus b. So it is equal to beta times a minus alpha. Yes, a minus alpha or a minus b. So am I right? Not. So C2 is this, or am I right? So I will check maybe. Or maybe it's better to so now y is equal to alpha minus beta a minus b times x minus a. It is better to represent it in this form, yes? And then we can easily find them. So this is the slope. Slope is alpha minus beta over a minus b. Okay. If x equals a, then this is 0. Okay, and must be alpha, so plus alpha. Okay. Yes. So if x is, if we substitute a for x, we will get 0, and so we must have alpha here. Yes. If we substitute b for x, we will get minus, so alpha minus beta multiplied by minus 1, so we will get beta. So this is our function. This is our function. Okay. So we can see that this is a linear function, and in what follows we will try to prove. So we need to prove that this is also this is only a necessary condition, yes, for the function to be a minimizer. But we need to check that it is actually a minimizer, not maximizer, or not. It may not be. It may be a saddle point, not a minimizer, right? It may be a minimizer, maximizer, or a saddle point. And usually we will do the following. So now I will try to. So I will consider. So I will consider task, and I will show you how to prove that it is actually a minimizer or a maximizer. Okay. Now So maybe we will consider an example, and after this we will try to apply our method to this problem. Yes, let's consider the following problem. So this is an example. Let it be task number 1. Here we will try to solve the following variational problem. The integral from -1 to 1 e to x y prime squared plus 6y squared dx. We must find the minimum. And these are our boundary conditions. Okay, so this is shine. So do you know what is this function? Shine or yes. Do you know this function? Huh? Shine. Hyperbolic functions. So have you studied hyperbolic functions on calculus? Polo and Kathy, do you know shine? Shine A? What is Okay, so shine X or using so another notation, hyperbolic function is equal to e to x minus e to negative x half. Okay, so on a graph, yes. So if we consider cos h, e to x plus e to negative x half, so these two functions look like our trig functions or circular functions. Yes, if you know circular functions cos x and sine x, they satisfy the following property: cos squared x plus sine squared x equals 1. Okay, and we can visualize these two functions, sine x and cos x, trig functions, as follows. We draw the unit circle centered at the origin. Yes, and for a given x, for the argument, so they are circular functions. So for the arc, if arc is x, then the first coordinate will be cos x and the second will be sine x, and they satisfy this property. Yes, but hyperbolic functions satisfy not this property but similar property. So the property of the form, so cos squared x minus sine squared x equals 1. So to visualize these functions, we should consider a hyperbola, the only right-hand branch, right? The right branch of the hyperbola of this form. Do you know the so that what is it? Hyperbola. What is hyperbola? No. So analytic geometry. So no calculus, no analytic geometry. You know nothing about hyperbolic functions, hyperbolas. Yes. Okay. What about state exam? Okay. So cos and sine both live on the hyperbola. So this is the equation of the hyperbola: x squared minus y squared equals 1. The equation of a hyperbola, second order curve or okay, or conic section, conic section. Hyperbola is a conic. Okay, well, so like for the circle functions, we should draw one branch, right branch of the hyperbola, and a point on a hyperbola corresponds to, so two coordinates of this point will be cos. So cos x and sin x. Where x is, what is the argument of these functions? The argument. So the argument of trigonometric functions is the arc length, and what about this case? The argument is an area. An area. So this part. Okay, the area. This area is equal to x half. Is the area. This is the argument. Yes. Okay. Hyperbolic functions. So they look like circular functions, but some operations are reversed. So the sum of squares, and here we have the difference of squares. Yes. The formulas for so double angle formulas. In some sense, they're almost the same as the formulas for the trigonometric functions. For example, sin 2x is equal to 2 sin x cos x. But for the hyperbolic functions, sin 2x is equal to 2 sin x cos x. So the same formula, double angle formula, yes. And for so cos 2x, do you know the formula for cos 2x? What is it called? So Daniel, do you know how to compute cos 2x given?
No.
I've forgotten. Cos x squared minus sin x squared. But here we have 4 squared x, not minus but plus, because minus, if we take minus, we will get 1. So plus sin squared x. So these are hyperbolic functions, and they are widely used in physics, maybe, yes. In relativity theory, they came from relativity theory. You know nothing about relativity theory. Difficult. Yes. Well, okay, let's try to solve. So sin 5 is, so I will write it. So sin 5, what is sin 5? E to 5 minus e to negative 5 half. Anyone know? Okay, and so 2 e squared times e to 5 minus e to negative 5 half is equal to e to 7 minus e to negative 3. Just this. Have you discussed hyperbolic functions in calculus?
Maybe we did, but
And what about you, Paul and Cassie? Do you remember anything from calculus? From calculus? Okay. Well. So we will start with the Lagrange equations. They look like dl over dy minus d over dx dl over dy prime equals 0. So we will start with this. And first of all, we will need dl over dy. What is dl over dy? How to differentiate this with respect to y, not 0, because this function depends on y times 12y. Yes. And next, so I will check the okay, I will check the function. Right, next, dl or dy prime. Daniel, can you differentiate with respect to y prime? Okay, and what is it?
Might not,
Sorry?
might not be right.
Okay, but try, please. E to x doesn't depend on y prime. Yes, we need partial derivative. Not total derivative, but partial derivative. E to x times
2y
2. Yes.
And then does y depend?
Okay, no. Only partial derivative. So when we take a partial derivative, we have 3 variables, x, y, and y prime. But when taking total derivative with respect to x, we should take into account that x is an independent variable and y prime and y depend on x also. Yes, but for partial derivative, we will not care about, we don't care about so y and x, so they are constants in this case. Well, so this is dl over dy. Well, next we need to find total derivative with respect to x. So we must take this and differentiate with respect to x. Take the total derivative, so it's better, I think, to write it as d over dx. What is the total derivative? So for partial derivative, x and y prime are 2 independent variables, but for total derivative we must differentiate the first part, so it will be e to x times 2y prime and plus e to x and differentiate this with respect to x. It will be 2y double prime. Well, and next we should construct the equation, Lagrange equation. Will be, so d over dy will be e to x times 12y minus this expression. Next, can we divide by e to x? So this is the common factor, and 2 e to x. And we will get 6y minus y prime and minus y double prime equals 0. And next we are trying to solve this differential equation. Y double prime plus y prime minus 6y equals 0. Okay, how to solve it? What?
Characteristic function.
Character. And can you dictate?
No.
What is the characteristic equation?
Oh, so it's going to be 6 minus lambda minus
The squared.
Oh,
Plus. So this one. Lambda squared plus lambda minus 6 equals 0. And the roots? 3 and 2, yes. So it will be a negative 3 and 2. And so the general solution is y equals c1 e to the power negative 3x plus c2 e to the power 2x. And next, what shall we do next? Is it the answer or not? No. So we must use these initial conditions. So y of -1 must be equal to 0. So y of -1, if we substitute -1 for x, we will get c1 e cubed plus c2 e to the power -2. It must be equal to 0. And y of 1 equals this, yes? c1 e to -3 plus c2 e squared equals e to 7 minus e to -3. We must solve these equations together. C1 is -1 or just, well, now we will, let's multiply this by e cubed and this by e to -3. Yes, and we will get, and then add them together. So we will get c1 plus c2 e to -5 equals 0. c1 plus c2 e to 5 equals e to 10 minus 1. Then subtract, and we will get c2. C2 will be, so if we subtract, so we will get e to 10 minus 1 over e to 5 minus e to -5. Okay, or if we multiply, so e to 5, e to 10 minus 1, e to 5, and then this is C2, and C1 can be obtained from this equation. It is -1. It's -1. Well, so our function is the following. Y equals, so C1 is -1, so minus e to -3x. And C2 is e to 5 plus e to x plus 5. Well, I will. Okay, it's this. Next, well, so this is the answer to the Lagrange equations. Huh?
There's more?
More, yes, yes. So we must minimize, we want to minimize this function. But now this is only a critical point, but it can be a local minimum, a local maximum, or neither, or a saddle point, for example. Yes. Right. Let's try to to check what convex or right. We must check this function. We will try to do it. So we will try. We will make a direct substitution because we have no other test, no sufficient condition. But we will try to find the difference. So I will remove this part. We will consider variation. We will try to find the difference. So suppose this is, call it j of y. Okay. Well, and now we will try to find j of y plus some function v minus j of y. But so where y is this given function. Let's try to find this difference. It will be the integral from -1 to 1 e to x, y prime, it will be y prime plus v prime squared plus 6y plus v dx minus the integral from -1 to 1 e to x y prime squared plus 6 to squared dx. And now we will try to find the difference. Okay. We may have a break and next continue on during the seminar. Yes. So we will finish this exam. We will complete this example, this task, and we will try to solve some task of this kind. Yes.